What's up, scholars? Today we're going to talk about biconditional statements. So let's think about what we know about the word biconditional. What's bi mean? It can mean two or both. We're going to use the both version of that. And a conditional statement was our if-then, remember? If-then statements. So we're going to have if-then statements that work in both directions. So we'll have if-then, and then we'll flip it around, and the reverse will be true as well. Okay, before we get into that, we need to remind ourselves of a couple definitions. Like perpendicular lines, two lines are called perpendicular if they intersect to form a right angle. Two lines are called perpendicular if they intersect to form a right angle. We have a very special symbol that means perpendicular. An upside down capital T means perpendicular. And we will indicate that lines meet at a right angle. So here's some lines that are crossing each other. They're meeting at a right angle with a right angle symbol in there, a little box. If there's a right angle here, then we actually know that the angle adjacent to it is also a right angle. We got two angles that together make a straight line. A straight line is how many degrees? 180. So 180 minus this 90-degree angle means this also is a 90-degree angle. And that's also a 90-degree angle, and that's also a 90-degree angle. So all of those are 90-degree angles. But we only ever use, or we mostly ever use, one right angle to indicate that they're perpendicular, even though all four are actually right angles. Sometimes that's a really useful fact. Cool. So, what does it mean to be perpendicular to a plane? Well, a line that's perpendicular to a plane, a line that is perpendicular to, let's use that symbol as much as possible, because perpendicular is a long word, and I'd much rather use a beautiful symbol. So a line that is perpendicular to a plane, you guys remember what a plane was? A flat surface, right? Like this is a flat surface right here. So a line that's perpendicular to a plane or a flat surface is a line that intersects the plane in a point. Surely that should say at a point. So the line intersects the plane at a point and is perpendicular to every other line in the plane that it intersects. Just like we talked about above, the symbol upside down capital T is read as perpendicular to. Alright, so we have some examples here, and we're going to insert our right angles where it makes sense. We have, it says, N is perpendicular to M, and then it gives us this picture of two lines. So let's call this guy line N. This guy will be line M. And this is introducing a new way to name lines that we haven't talked about yet. If you have one lowercase cursive letter, that also indicates a line. So these are lines. If line N is perpendicular to line M, what does that mean? It means they intersect to form a right angle. So let's make that explicit with our right angle symbol. Now we see line N and line M meet at a right angle, meaning they are perpendicular to each other. And we've got line N perpendicular to plane P, so let's call this line N. This will be our plane P. All right, so this lowercase cursive letter, that's a line. An uppercase single letter here is our plane P. Really should be in cursive. Do you guys still learn cursive in class? I don't even know. I did. All right, line N is perpendicular to plane P. What does that mean? It means the line intersects the plane at a point and is perpendicular to every other line in the plane. So this line N is perpendicular to this plane. Means they meet at a right angle. And any line I would draw that goes through this plane, those are going to meet at a right angle. Right. This would meet at a right angle. 3D drawings here. Any line that goes through this plane meets at a right angle with the line. This is kind of like, see if I can do a demo. I have, let's call my pen is going to be a line. Pretend like it goes on forever, the infinite pen. And then my plane will be this piece of paper. So I have my line and my plane. I'm going to draw a bunch of lines on my plane. Guess I could show you what I was doing there. That's what I did. Drew a bunch of lines. Yeah, this makes more sense. Okay, now I'm going to take this pen and make it perpendicular to my plane. That's this flat paper. There's a bunch of lines on it. I'm going to turn this a little bit sideways so we can see. Maybe I'll bring it over here in this video. Okay. This pen is my line, pretend it goes on forever, is perpendicular to every single line that it intersects. Every single line it goes through. Every single line that it intersects, they all meet at a right angle. They all meet at a right angle. Cool. All right, so let's look at some examples on our paper. Example number 1, decide whether each statement about the diagram is true. Explain your answer using the definitions that we've learned. Ooh, cool, we get to remember some definitions. It's great. Example 1A, points D, X, and B are collinear. What did collinear mean? In a straight line. Right, co meant together. So are they together on a line? Are they together on a straight line? X or D and X and B, D and X and B, do they all lie on the same line together? Yes. Yes, they are. D, X, and B all lie on the same line. Right? They're all on the same line. When B is line AC, right? It's got arrows on each side of that symbol on top, so that means it's a line. Is line AC perpendicular to line DB? What did it mean for lines to be perpendicular? It meant that they intersected. Let me scroll back up here. Perpendicular lines intersect to form a right angle. So do line AC and line DB intersect to form a right angle? Of course they do. That's what that little box means. That means it's a right angle. Yes. They intersect at a right angle. And finally, Is angle AXB adjacent to angle CXD? What did adjacent to mean? It means they are next to each other. They're right next to each other. They share a side. Share a side. They're really good buddies. They share a side. They're like Siamese twins. They share a part of themselves with the other one. So angle AXB is this angle right here. Angle AXB makes that angle here. And angle CXD is over here. These guys share any sides? AXB and CXD, they share the point in the middle, but they don't share any sides. So no, they don't share any sides. They don't share any sides. What are those angles called to each other? Because together, their sides make a straight line. Their sides make a straight line. And they're right across from each other. They're actually vertical angles. They are vertical angles. They're not adjacent. They don't share sides. They're right across from each other. They're vertical angles. This is good practice remembering some of the definitions we talked about a while ago. Great. You guys are doing great. Let's keep cruising. All right. Yay, fun times. Using biconditional statements. All right, so conditional statements, again, those are if-then statements. Like, if you come to math class, then you'll have the best time. If-then statements. Conditional statements are not always written in if-then form. Sometimes you'll see them in only if form. Right? Like, the match is burning only if there's oxygen in the room. Well, which part of this is the hypothesis and which part's the conclusion? Or the hypothesis came after the word if. So, there's oxygen in the room comes after the word if. That's going to be our hypothesis, which we abbreviated with the letter P. Very good. If there's oxygen in the room, so there's oxygen in the room is the hypothesis. Then the match is burning. That's our conclusion, which we abbreviated with which letter? Q. Awesome. So let's rewrite this as a if-then statement. If there is oxygen in the room, if there's oxygen in the room, then the match is burning. The match is burning. Yeah, what do we need to make fire? We need oxygen and we need fuel. So the match is the fuel, that's the wood, and then you need the oxygen for it to burn. Yeah. All right, a biconditional statement. Remember we said bi is going to mean both in this case. Biconditional statement is going to be a statement that contains the phrase if and only if. If and only if. Writing a biconditional statement is equivalent to writing the original conditional statement and its converse. So it's equivalent to writing the conditional statement and its converse. Cool. Biconditional statement, you know it's biconditional if it has the phrase if and only if, which we are going to abbreviate because we are math magicians. We love abbreviations as IFF. That'll mean if and only if. And writing a biconditional statement is equivalent to writing the conditional and its converse. Cool. Our symbolic form of the biconditional statement is going to be P, and then an arrow that goes both ways, Q. Meaning we could say if P then Q, that's our conditional statement. And we could also say if Q then P, that's our converse. Let's write that. That's our conditional and our converse. Cool. All right, let's look at example number 2. Rewrite the biconditional statement as a conditional statement and its converse. Well, this says 3 lines are coplanar. What does that mean again? Oh, right, in the same plane. In the same plane. So 3 lines are coplanar if and only if. That's how we know it's a biconditional statement. It says if and only if. They lie in the same plane. So, since the biconditional statement is equivalent to writing both the conditional and the converse, it doesn't matter which order you say the first one. So we could say, if 3 lines are coplanar, then they lie in the same plane. Let's call that our conditional statement. If 3 lines are coplanar, then they lie in the same plane. Our if-then statement. And then our converse means we just flip those things around. Say the first one first. Nope. Say the first one second and the second one first. So we're going to say if 3 points lie in the same plane, then they are coplanar. If 3 points, no, not 3 points, if 3 lines, there we go. If 3 lines lie in the same plane, then they are coplanar. Okay, if 3 lines lie in the same plane, then they're coplanar. We took the original conditional statement and flipped the hypothesis and the conclusion. Cool. A biconditional statement, just like all of our other statements, can be true or false. If they're going to be true, though, both the conditional and the converse have to be true. Both the conditional and the converse have to be true. It has to work both ways for it to be true. So let's look at this example. Consider the following statement. X equals 3 if and only if x squared equals 9. Is this a biconditional statement? Well, yes, it has the phrase if and only if in it. If and only if. Yes, it contains if and only if. See, using our abbreviations. Is it true? I don't know. Let's check. Let's look at the conditional statement. Let's say if x equals 3, then x squared equals 9. Is that true? I mean, yeah. X squared, if x is 3, would be 3 squared, and 3 squared equals 9. This is true. Let's look at the other one. If x squared equals 9, then x equals 3. Is that true? If x squared equals 9, does x have to equal 3? No. Why? Because negative 3 squared is also 9. So this is a counterexample where another number makes the hypothesis true. So this is our counterexample. Counterexample that proves that this statement is false. So if x squared equals 9, x does not have to equal 3. It could, but something else could work too. So is this biconditional statement true? No. The conditional was true, but the converse was not true. So the biconditional is not true, because both parts have to be true. Okay, you guys are doing great. Doing so good. All right, example number 4. Each of the following statements are true. Write the converse of each statement and decide whether the converse is true or false. If the converse is true, combine it with the original statement to form a true biconditional statement. If the converse is false, then state a counterexample. All right, you guys are going to do that. You can use the last example as an example. So you're going to do part A and part B. Knowing how to use true biconditional statements, things that work in both directions, is an important tool for reasoning in geometry. Reasoning in geo. For instance, if you could write a true biconditional statement, then you can use the conditional statement or the converse to justify an argument. So, for example, the converse of the angle addition postulate is true. Write the converse and combine it with the postulate to form the true biconditional statement. So the angle addition postulate, which we did a while ago, says if P is in the interior of angle RST. I'm just going to draw that out right now. I've got angle RST, angle RST, angle RST, and it says P's in the interior, so P's in the middle somewhere. Doesn't have to be exactly in the middle. Then the measure of angle RSP, so let's go ahead and draw that guy in there. Angle RSP is this first angle, RSP, plus the measure of angle PST equals the measure of the big angle RST. All right, that was our angle addition postulate. If we had two angles that were adjacent or right next to each other, we could add up their measures to find the big angle. Right? Like if angle RSP was 25 degrees and angle PST was 5 degrees, we would know that the angle RST, that big angle, RST equals those two added up, which equals 30 degrees. That's what our angle addition postulate says. So what's the converse of this statement? We're going to flip around our hypothesis and our conclusion. So we'll say if the measure of angle RSP plus the measure of angle PST equals the measure of angle RST. So we're writing our conclusion first as our new hypothesis. If that statement is true, then P must be in the interior of angle RST. Then P is in the interior of angle RST. P couldn't be out there somewhere in the wild. It has to be in the middle. How do we write this as a biconditional statement? Well, we say we can go in either direction. We could start with this as our hypothesis. That is the conclusion. We just got to put if and only if in the middle. Doesn't matter. So we'll say P is in the interior of RST if and only if the measure of angle RSP plus the measure of angle PST equals the measure of angle RST. P is in the interior of angle RST if and only if the measure of angle RSP plus the measure of angle PST equals the measure of angle RST. Et voilà! Ça c'est bon. Très bien. All right, scholars, that's it. Keep on that hustle. I love you. I'll see you next time.